Okay, so the first news is we're going to do the first quiz next week. Um, so quiz 1 is going to be on Monday. So remember, the quizzes are just short answer questions about stuff I've said in class. It's not going to be any calculations or anything. Um, but I could ask you about rules, about vectors, or uh, any of the stuff that I say. We're going to get into particle statics today, so stuff I say about that. All I'm trying to do with these quizzes is to get you to read and reread your lecture notes. Okay, and just try to remember what I say. Yep.
Professor, for the 829 homework, do we go over problem 19?
Yes, for sure. Which one?
Problem 19.
Okay.
The beam and angle. I got confused by why it tells us 20 degrees. I thought, because it doesn't give a distance to the 20 degrees.
Okay.
Then one type of it.
Whoops, that's the wrong one. Oh, yeah. Yeah. So number 19. This beam, so it has a length of 4. Let me just write some of this stuff in. So we know that the length here is 4. And we know that this angle is, let me move that up, just make it less cluttered. This angle here is 45 degrees. And then we know that the slot here makes an angle of 20 degrees with the vertical. And so the first thing we want is we want to come up with a vector that's perpendicular to the slot. This is actually something that's going to be really useful for us because it turns out that the force that slot applies to the pin, what's attached to it, is going to be perpendicular to the slot. There are 2 vectors that are perpendicular to the slot. I have 2 unit vectors, 2 directions perpendicular to the slot. And either one of those 2 is fine. But I just want you to be able to visualize that, understand that. So one perpendicular is this way, and then the other perpendicular is this way. And so the answers you get from those 2 different vectors will, the magnitudes of the components will look the same. They'll just be negatives of each other. Okay. So I guess I'll do the one that's opposite of the one that I did in the solutions. All right, so what's a vector with a magnitude of r perpendicular to the slot? So I'm going to choose my perpendicular vector to be like this. Okay, so it's going to be 90 degrees from the slot. And in order to in order to calculate the components of that unit vector, because this is going to have a magnitude of r, but we're going to do it by calculating the unit vector and then just multiplying it by r. I'm going to use that piggybacked angles idea. So I'm just going to go from some given reference to a vector representing the slot, and then from the vector representing the slot to that vector that's labeled r there. And that's the piggyback, is like having that intermediate point of the slot. So I'm going to start with, okay, so this is A. I'm going to start with my coordinate system. And the vector that I'm going to choose to represent that slot, I want you to notice that I really could choose, again, I could choose two different vectors to represent that slot. I could choose one going up that way, or I could choose one going down that way. Okay? And this stuff would work out fine either way. I'm going to, since I drew that 20 degrees as being drawn from like a vertical, an upward line, I mean, I'm going to choose that reference vector to be like this. And I know that this is 20 degrees, this angle here. And then my second vector is going to be perpendicular to this, so it's going to be this way, and this angle is going to be 90. And this angle was 20. So now to get the unit vector components, I'm going to start at the positive x-axis, and I'm going to go 90 degrees this way to get to the vertical line, the positive y-axis. Then I'm going to go 20 again. So for coming up with this angle theta, I'm going to start counterclockwise 90, so that's plus 90. I'm going to go counterclockwise another 20. And then I'm going to go counterclockwise another 90. And I get an angle of 200 degrees. So that should, like, our unit vector is going to be the cosine of 200, sine of 200. And I think that gives negative 0.940, negative 0.342. Now that we have the unit vector, now we just multiply by the magnitude. So the force vector is negative 0.940 times r, negative 0.342 times r. If instead I had taken the other perpendicular to the slot, it would have been going this way, and it would have been, 90 degrees from the slot this way. So adding up that angle, I would have gone counterclockwise 90, counterclockwise 20, but then clockwise 90. So I would have gone 90 plus 20 minus 90. My angle would have been 20, and I would have gotten positive 0.94 r, positive 0.342 r. But they work equally well in the problems. Yep.
And for B, because it's 45 degrees, we just do the 45 angle triangle. We get 2 root 2 and 2 root 2.
Well, the one thing you have to think about is
Negative.
Are we right? Exactly.
Because it's downwards.
Yes, because so we want the vector that goes from the wall pin to the slot pin. So we're looking for this vector. And so for that, I guess you could think of it as like I'll draw the first one just because this is the way I have that angle drawn. It says that it's 45 degrees from the horizontal to there. And then the vector we want is in the opposite direction. So now this angle is 180. So we have positive 45 plus 180 is 225. And so the unit vector is cosine of 225, sine of 225, which is 0.7071 negative and negative 0.7071. And now multiply those by 4. Do I know what that is? 2.8. Negative 2.83, did you say?
Yeah.
Negative.
2 root 2.
Okay.
Negative 2. Thanks.
Yeah. Any other homework questions? All right. That's it for the vector review. So now we're going to get into particle statics. So what is a particle? I think a lot of people tend to think a particle is something that's really small because you think of subatomic particles or whatever. It's not necessary that particles be small. Just think of a particle as a mathematical simplification of things. So it's a simplification where the object has no length dimensions. And since it doesn't have any length dimensions, you can't make any distinctions between different sides. And so there's no way to talk about the orientation of the body. You can't say now it's facing this way, now it's facing this way. So all you can talk about is its location. It only exists at its center of mass. Okay, particles don't have length dimensions, but they do have mass. That's not really going to be an important thing in statics, but that's an important thing to understand about particle calculations. For particle calculations, one thing I want to say about that. You can use particle statics to represent any point on a system that's in static equilibrium.
Can you scroll up a little bit so we can see, yeah, just so we can see the full definition of.
Yeah. Sure. Most of the time in this class, we're going to treat bodies as rigid bodies, not as particles, but there'll be a few things where this is useful. There's only one governing equation for particle statics. And that is Newton's second law. I'm always going to abbreviate that N2L, Newton's second law. And Newton's second law says add up all the forces on a body. It's equal to the mass times the acceleration of the center of mass. For us, since everything we do is going to be in static equilibrium, the center of mass has zero acceleration.
What is static equilibrium?
It means that there's no acceleration of the center of mass. So center of mass has, right, exactly. And so the governing equation just says the net force is equal to zero. So that's it. Notice that this is, so how many equations does this give us, this single vector equation? If we're doing a two-dimensional problem, this is two equations. And in a 3D problem, it's three equations. Just the three different components. Anytime in this class, in any class really, but I don't control you after you leave this class, but anytime you use Newton's second law or the moment equation that we'll get to in not very long, you need to draw a corresponding free body diagram. This is an abbreviation, free body diagram. So here is the way that I want you to draw free body diagrams. Like in physics 1, pretty likely you got used to drawing free body diagrams as a dot with arrows going out in the different directions. We're going to start putting a little more effort into, it doesn't have to be art, but we're going to put a little more effort into drawing the outline of the actual body. And the reason we're going to do that is that most of the time we're going to be dealing with rigid bodies where we have to calculate moments and stuff. And so the physical location where forces are applied is going to matter. In physics, when you were mostly doing particles, the physical location of forces didn't matter. It didn't change the problem. Okay, so here are the steps for drawing a free body diagram. So first, draw a closed outline of the chosen body. And this should have no external objects in it. And no internal details. All you're trying to do with this outline is draw a very clear distinction between stuff that's in the in crowd and stuff that's out of the in crowd, you know? Like if you're isolating a car, then you'd have the outline of the car. You wouldn't draw anything about the street that it's sitting on. You wouldn't draw the windows or anything because that stuff is all included. All we want is an outline that separates what's in from what's out. Second, draw all load vectors. I'm making a distinction. When I say load, I'm saying load instead of force because this can include forces and it also includes couples that we'll talk about in a week or so. Okay, so how do you draw the load vectors? Well, first, if the direction of the load is known, then draw an arrow in that direction. And label it with a scalar. Scalar is like a number as opposed to a vector. Value or variable, usually a variable. So if you know the direction of a force, then the only thing you don't know is how long the force is. You know everything else about it. And so you represent what you don't know about it with just a single value, a single variable like r, f or something. It's not a vector. You only have one unknown. And if, on the other hand, the direction is unknown, so if the direction of the load is unknown, draw vectors in each coordinate axis direction. Like basically you're just drawing a little thing that looks like a coordinate system. And then you're going to label it with a vector variable or value. So like for part A here, if the direction of the load, you know it's going this way, you draw an arrow in that direction and then just give it a single letter name, not a vector name. Whereas for part B, if it's in 2D, you could label something like this and give it the name R. If it's in 3D, you could give it something like this and label it whatever. Doesn't have to be R, but it has to be a vector. Okay, sometimes these are going to get pretty complicated. So I think an important question to ask yourself is, how do you know when you're done? How do you know when you've finished putting everything in that, all the forces in? How do you know when you've represented all the loads? Well, there are only two types of, there's like two, you can think of them as like categories of forces. We're always going to have weight. If there are any other field forces, put those into. In this class, I don't have any problems that mention other things like electric fields or whatever, but those would sort of go in this category. And other field forces. And then once you've done that, the only other type of loads are due to contacts with the surroundings. So just mentally go around the boundary of your chosen object. So go around the boundary of the free body, looking for points of contact with the surroundings. Once you have loads for each one of those contacts, you're done. So once you have the loads for each contact point, you're done. Okay, so let me show you what this looks like. So let's say we're like forensic physicists and we show up to a crime scene and it looks like this. There's like mud, quicksand, something. And there's a pickup truck that's like submerged partially in the mud. And there's a person standing on the truck, strangling a giant bird. Look how mad this guy is. Okay, and there's a rope attached to the truck, and a helicopter is trying to pull the truck out. That's in there because I have this good way to draw helicopters. And then there's a tether on the bird's leg, and it's attached to a fish that's like trying to swim away. Okay. And we're assigned to do a calculation that deals with like the forces applied to this truck. Okay. So we want to draw a free body diagram of the truck. We might be interested in what's happening to the fish, but we're paid to deal with the truck in this case. So that's what we're doing. Okay, the steps of drawing a free body diagram. We're first going to draw an outline of the truck. It doesn't have to be art. Let's say it's that flatbed truck. And now we're going to include the weight. We'll assume there's no magnetic fields or electric fields doing anything important. So the weight acts at the center of mass of the truck. We'll talk later about calculating centers of mass, but let's say it's somewhere there. And so this is the mass of the truck times 9.81 acting down. Okay. And now we're just going to go around the boundary of the truck mentally, and we have to represent all of the contact points between the boundary of the truck and the surroundings. So let's think about where there's contact between the surroundings and the boundary. So I'm going to start over here at the rope that's connected to the helicopter. That's a pulling force from this cable. We're gonna spend a lot of time talking about how we know what types of loads different contacts apply. But this is a pulling force. You've done cable stuff before. I'm just going to call this a force T that's in the direction of that rope. Okay. Next, if I'm going around sort of counterclockwise around the boundary, the next thing we get to is the person. Okay. The person, we don't know exactly what the direction of the force is that person is applying to the truck. So I'm going to just put this as an unknown force. We're doing this as a two-dimensional problem. So I'm going to put this in as a unknown force vector. That's why I drew this as kind of like a coordinate system. It's an unknown direction. And I'm going to call this force vector the force applied by the person. Okay. Then we have the same deal with the bird. We don't know the direction of that force. So I'm going to draw the little coordinate system, and I'm going to call this force vector force from the bird. And then last, we have loads applied by the mud. And so I'm going to just treat that as an unknown force vector. So I'll call this force from the mud. Yeah, good question. So remember that what we're doing here, all we're doing is going around the boundary of whatever we chose and looking for contact. So it's not that fish doesn't influence what's happening here, but whatever that fish is doing only applies to the truck through the contact force of that bird. Okay. And so now I've gone around the boundary. I've represented a load for every place that the surroundings make contact. And so I know I'm done. Okay. And so obviously you look at this and your brain kind of wants to just short circuit and say, like, there's too much going on. I can't make sense out of it. But this is a very systematic way to say, like, I don't have to worry about everything. I just have to go through the steps, represent the weight, represent the contact points, and then little by little we'll start working towards a calculation. Okay? Okay, here are the types of contact forces that we're going to deal with. So this was generally for free body diagrams. We're going to go through these steps for all the problems we're going to do in this class. But now we're going back to particle statics. So here are contact forces. With known directions. In particle statics. So the first one is going to be cables and slender rods. We're going to treat these similarly. The second one is going to be frictionless contact. And then the third one, well, I said that this was known directions. I'm going to put friction contact in here, but we'll see that really what that is just a force with an unknown direction. So the first one is cables and slender rods. So these apply a force to the body that's parallel to the cable or the rod. And away from the chosen body. So that's how we're going to draw it in the free body diagram. If we're talking about cables, a cable, then the magnitude, or that's the wrong word, the value needs to come out positive. And the reason for that is we're assuming that this cable is in tension, and cables only can support tension. You know, you can't use a string to push on something. Okay. So this is because cables only support tension. For a slender rod, the value can come out positive if the rod is in tension, or a slender rod can also, you can push on things with a rod, and so it can come out negative. But if it's in compression. Okay, so let's do an example here. So let's say we have a pulley attached to the ceiling, and one side of the pulley is attached to a mass M1, and then the other side of the cable is attached to a mass M2, and let's say this is connected to, I want that to be straight. Let's say this is connected to the ground by a slender rod. Okay. So I want to draw free body diagrams of both of these masses. So first, a free body diagram of M1. I'm going to draw the outline of the body. There's a weight force acting down of M1 times 9.81. I'll just write that as M1G. And then the cable applies a force parallel to the cable away from the body. And I'll call this T. So that's it for that one. And then a free body diagram of M2. There's an outline of the body. There's a weight down of M2 times G. There's a cable force that's parallel to the cable away from the body. Yes, they are, because it's the same cable. And then we're going to treat the slender rod the same way we treat a cable. I'll call this F instead. But that is going to be parallel to the rod, away from the body. The only difference is when we do our calculations, if we calculate a negative value for T, we know something went wrong. If we calculate whether we calculate a positive or a negative value for F, that's a reasonable thing to get. Because the slender rod can either pull on something or it can push on something. Yep.
So for this one, it's static, it's not moving?
Right. Yep. These rules for free body diagram work for dynamics too. This is exactly how you'll do free body diagrams for dynamics, but the calculations will all be statics.
That is why this class is called static.
Yep, makes sense to me. Okay. Cable section.
Professor?
Yeah.
So if it's not moving, right, wouldn't F need to be 0?
Yeah, you're right in this case. But if it is moving, then you don't know.
Yeah.
That's right, though.
Because it's not.
Exactly. Yeah, I mean, if you need those three things to add up to 0, that F1 has to be 0. I just want to say one more thing, and then I'm done for today. So notice, for a single cable, even if it's passing through pulleys, the magnitude of the force and the magnitude of this force is called the tension, that it applies to all contact points is the same. So that's why we knew that the magnitude of these two forces in these two different free body diagrams, we had to give it the same name. Okay, but we'll get a lot of practice with that. And I know you've seen that stuff in Physics 1. Any questions? Okay, that's all for today.